Should we get started or what?
Hello? Excellent. So, here we are at Edit This Page, Scaling the Wiki Beyond 1 Million. So, some of you may be wondering, what is a wiki? If so, shame on you. You should know by now. Basically, it's just a little website where you let the members of the general public edit your website for you, which is an interesting way of doing things, which many people think probably shouldn't work because there are a lot of very silly people out there who will not really produce good work. But there are also a lot of people out there who do produce very good work, and hopefully they outnumber the people who are causing trouble, and on the whole, something good comes out of it. And that brings us to Wikipedia, but first we have to start with Nupedia, which was its predecessor. And that was a little site that internet entrepreneur, Jimbo Wales, came up with as a little way of giving back. He made a encyclopedia project running under an open content license, but it was going to be created by real academics, and every article would go through a complicated review process to make sure that they were actually any good. Unfortunately, it was pretty slow going and only came out with about 28 articles after its first year or so of operation. I'm actually not sure of that exact number because at some point we lost the database and no one really cared because no one missed it. So that now brings us to Wikipedia, which was originally a side project of Nupedia, a little extra board where people could just sort of throw articles together really quickly. And the theory was that you would take these articles being generated by wackos on the internet and basically use them as notes for creating the real articles in Nupedia. That never really happened. Nupedia has died a very sad death, and Wikipedia has grown and grown and grown and grown. And today Wikipedia has over 1 million articles. 90% of them are probably about Pokemon or something, but there are a lot of really good articles in there, which one would hope given the sheer number of it. So whatever anyone says about the quality of Wikipedia, there's no doubt as to its quantity. Today, there are projects available in many languages, several different projects. One aims specifically at a dictionary system, quotations, and now a media system for mainly open content photographs and also sound and video files. And just to make sure you don't mix these up, because everyone, including us, does, and this is entirely our fault for choosing cute names. Wikipedia is the encyclopedia. Wikimedia is the nonprofit foundation that runs it, and MediaWiki is the software that runs all these wikis. It's really unfortunate that we chose these names because we constantly get bug reports about their Wikimedia being unable to run Wikipedia with their... Anyway, I don't even know what's going on. Back in the early days of Wikipedia, which started in January 15th, 2001, we ran on an existing wiki system called usemodwiki. This is actually a single file Perl script. It's very simple to get set up and started, which is, I suppose, why it was selected. And it has a pretty bare bones user interface, as many traditional wikis do. And the main problem with it as things continued to grow and the wiki approached 10,000 or 20,000 articles, even after its first year, was simply dealing with the sheer amount of stuff. You'd have articles which had hundreds and hundreds of revisions, all of which we store, which creates a lot of data to deal with, and the data would be sometimes subtly corrupted when the file system storage wasn't quite handled right, locking didn't work, search became a big problem. So a nice fellow named Magnus Mansky, who's probably here somewhere, there he is waving, wrote up a new wiki system just for Wikipedia, which had no name for a long time. It was written in PHP, which maybe is not the greatest language in the world, but it works, and it's better than Visual Basic. And using, instead of the file system backend, the data is all stored in a Mysql database. The main advantage of using some sort of database was that you can do ad hoc or reasonably structured queries on that database to get more organizational information. As we get to 10,000, 20,000, 100,000, a million pages, it gets very difficult just to deal with the amount of stuff. You see this problem, of course, in the grandest scale on the internet at large, where we have search engines like Google just to find anything at all. So the existence of a full-text search engine in MySQL was also a very useful part of that, in that we could actually get a decent search engine going out of it and produce automated lists of which articles connect to which, relationships between types of pages and categories and such forth. And this system was rewritten, well, mostly rewritten once by a fellow named Lee Daniel Crocker, who is now a professional poker player. And we've basically been working on that system ever since and hacking new exciting things into it to deal with exponential growth. This is a prediction of the number of pages that there would be in Wikipedia over the next couple of years. It has largely come true. In fact, I think we have even more than were originally predicted. And it follows pretty much a straight exponential growth graph. You see a little spurt there when somebody added 20,000 pages on every small town in the United States with the population, latitude, longitude, and area. Of course, with the growth in the number of pages has come a growth in the amount of requests that the web servers have to deal with. We have more users editing the pages, more random people visiting the pages who just come off of Google or some other search engine on some topic they were looking up. And we're getting up into the range of 1,000 requests per second, although that's not all actual pages. The downside of having a huge number of requests and no budget is that your software tends to bog down when you don't really have enough to handle it. So we've had intermittent problems over the years with insufficient resources and insufficient software, which we work on time over time over time. And that's basically what we're here to talk about. So what are the problems that make this a problem? The first is simply that we let people edit the site. So any site that you visit could change at any time. It may have been edited 1 second before you came to visit it. You may have just edited it yourself and now you're coming back to look at it. And it needs to be up to date. This means that caching is a little bit more difficult. We have to make every request check back with the server just to make sure that no changes have occurred, and then we have to deal with the amount of time that it takes to do the check. So we do save on caching, but not as much as we would like to. And of course, the edit of one page can impact many others As the status of the links changes, they have to change from one kind of link to another kind of link. That means we have to potentially invalidate 10,000 pages if someone creates or deletes a particularly popular page. And of course, we have all those stupid cute features that we wrote the new software for, which are really nice for collaboration, but mean that it's a lot more work to generate a bajillion page views per day, such as allowing users to customize the look of the site because they all complain about how it looks, and the ability to message directly to other users, which means that you have to check on every view for whether you have new messages, etc., etc., etc. So basically there are three roads on optimization. You can do less work, you can do more work at the same time and get it all done faster overall, or you can do the work itself faster. PHP, it's an interesting language. Like many scripting languages, it compiles to a bytecode, and then the bytecode is executed. The bytecode execution generally is fast enough for most purposes, but not as fast as a compiled system would be. But very often, the slowest part is simply that first compilation step, when it has to parse all your source code and turn it into bytecode. And by default, PHP does that every time you load a page. I think this is actually a scam by the PHP people to get you to buy their optimization software. And I suspect it works pretty well, because it really does help a lot to install one of those. There are also some open source versions, such as Turk Cache, which is what we've used on Wikipedia. And that takes all that compilation overhead and basically, boom, it's gone. So that at least improves a lot of the PHP slowness, although you still have runtime to deal with. Of course, we can avoid PHP entirely if we don't have to hit PHP, but instead can serve a cached page. And we've been using for the last year and a half or so a squid system, where we use the squid proxies as a reverse caching server, where each user hits the squid first, and the request then goes on to PHP only if either the page is not cacheable at all, because the user is logged in and has special options, or if the page has changed and so it's been invalidated from the cache. And because this is an internal cache, which we control, we can purge pages out of the proxy cache when they're edited, which is the main problem with the web client-side cache or an intermediate transparent cache system that some ISP may have, where we don't know that they have pages cached, so we have to tell their cache, don't keep these pages, and which is a general problem with dynamic data, unfortunately. The other possibility, of course, is simply adding more servers. When you have more servers, it doesn't matter how slow they are if you have enough. Unfortunately, servers cost money. So we set up a nonprofit organization, which is the Wikimedia Foundation, which is our second cute name. And basically what that is all about is setting out financial support for Wikipedia and related projects. And to date, a lot of that has been in getting our server farm system really off the ground and sufficient to the task. So about last year, we had such problems with our old system that it actually collapsed entirely for 3 or 4 days before we had the site back online, simply because we only had about 3 servers, and 2 of them crashed at the same time with hard disk problems and motherboard problems, and we were just sort of left gone. But now we've got a lot more. Even I don't know what all these machines do, or what this graph really means. But basically we have things divided up between the Apache servers, which are running the actual PHP script, the Squid cache servers, which handle most of the heavy load a lot faster, and then the poor little database cluster. Unfortunately, as we've improved things on the Apache and PHP side and with the Squid caching, we've found our remaining bottlenecks are in the database and in the additional file system areas where we have uploaded images. As people continue to add more and more images and get into adding large images for potential future use in printing, etc., where the large images have to be scaled down, you have to check whether they're there, yada, 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 which means that you have to load up the network file system, which is hideously slow and becomes a bottleneck as all those donuts ask one single server, do you have this image file? And it replies, yes, I have this image file, but it takes a while. But we have moved those to a second server, which is faster, and that's less of a bottleneck than it has been. But it is an area where we want to look at new solutions in the future. And then, of course, there's simply optimization of the code itself. Further, the database bottleneck has its own problems. So there's all the boring optimization rules that I'm sure you've heard about before. You take all the code that you run 5,000 times because it's in an inner loop, you move it to the outside of the loop. PHP, of course, doesn't have a very smart compiler. It doesn't do a lot of optimizations by itself, and even if it did, it wouldn't do things like that. And because of the parsing overhead, you want to remove loading code that you're not actually going to use. That's less of a problem for us, but there are a lot of people using MediaWiki for third-party sites where they might not have the bytecode cache set up. And we do care about third-party users. So when it takes 3 times as long to load the code as it does to render a page, we kind of want to work on that. So all these boring little things have been done over the last few months to some degree, which has basically doubled the performance for many tasks from the previous stable version 1.3 to the new beta version of 1.4, which we have recently put up on Wikipedia and will soon be released as a stable version, hopefully. Then, of course, there's our database bottleneck. Now, the structure of the system, as it was originally designed, the whole system had 3 tables: current page revisions, old page revisions, and user data. And that was really simple, seemed like a good idea at the time, and it worked pretty well for a while. But after a while, things become more demanding, and we added more additional tables, split off fields from those tables, or from blobs in those tables into their own separate tables, etc. Now, as it stands, we still have the same basic system, which is the current revisions and the old revisions. And one of the problems in this is simply that you have a lot of data in every record. Some pages are hideously long, especially discussion pages or the discussions about which pages should be deleted, or no, this should not be deleted, yes, it should be deleted, it should not be deleted, etc. This kind of goes on and on and on. And you might get several hundred kilobytes or more in a single page and hundreds of revisions of that. So then when somebody goes along and asks for the database to give information like what pages has this person edited in the last week, it has to go through those entire records. And that loads a lot of data and puts a lot of pressure on the I/O system on the database servers, which becomes more and more of a problem as it gets bigger and bigger. And we have reduced the load on the database to some degree with a replication slave system, where many queries can be handed off to a slave server which has a copy of the database, and the copies are kept in synchronization. But it's not perfect. They're still slow themselves, and there are general problems with the replication. MySQL's replication works by taking every query that changes the database and sending that entire query to each slave server. And if that query takes a long time to edit a lot of records, then you can actually end up with the slaves being behind, as it takes a minute or 2 minutes to update the same information. And then you end up with problems where the system's a little bit out of sync. People try to load up a page, they get the wrong version, or in the worst case, the replication system actually will break entirely. It's very fragile in its current incarnation, and it tends to take the easy way out. If it sees anything wrong, it just sort of stops. And then your database stops updating, and in an hour, you kind of go, we should probably fix this. So that's kind of a problem, and it's a limited issue. So one thing we do want to do is continue to work on restructuring the database into a more efficient set. And one of the things we're hoping to do in the next version, which should be released sometime in February or early spring, is to split up those large records into smaller systems, where each page, for instance, will have a small record which just has its title, some general information about whether it's restricted for editing, when it was last edited, which version was the last edit. And this record is going to be a lot smaller than the one that has 400 kilobytes of text in it. And then you want kind of the same improvement for each individual revision, where also you want to save the problem of duplicating information every time. Under the current system, when you save a page with a new version, it has to take the old version and copy that entire thing from the cur table to the old table, because it's not going to be in the cur table anymore with the current revisions. It's now an old revision. So that actually doubles the I/O requirements for updating on our current system. So that's something that we want to reduce. So the new system is going to be something that we would have done in the first place if we knew what we were doing. But because this is a wiki, we don't know what we're doing. We just sort of wander along as we go along, and by and large, things come out pretty well. So one of the big improvements that we're going to have on all those queries that don't use the text is not having to touch the text. Another issue, going back to simple execution speed, is maybe you can do better than PHP, but rewriting the entire system in C or C++ or even Java is faster than PHP would take some time and introduce a bajillion new bugs, and you don't really want to do that if you can avoid it. But what you can do is add particular issues in, or particular subsystems in one of those faster languages and call out to them when you need it. And one of the first things that we actually did for that was the Latex math equation subsystem, where there's actually a unit written in Objective-Camel, which we shell out to that. It sends the code through a parser, which checks it for safety, produces an HTML equivalent if it can, and then runs it through LaTeX to produce an image. And we're looking into having more additional faster systems, such as a new Diff subprogram, which will show, or we already, or blah, 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 blah. When you look at a revision of a page, you want to see what the differences are. So you bring up the Diff View, which runs through and finds all the paragraphs that have changed and finds all the words within a paragraph that have changed and highlights them so you can see what in this 400K page has actually changed. And that takes a while in PHP, particularly on the really long pages where somebody has changed every line of 4,000 lines. So you can do a lot faster in C++, and we have a PHP extension that someone wrote to do that, which of course would require that you have appropriate permissions on your PHP system to install an extension. So that limits us a little bit in that if it's a core component of the software, that there needs to be an alternative. With the Latex system, it's not a core component, it's a neat additional thing. So it's okay if we don't have a pure system. But any third-party user of the wiki who doesn't have the ability to run or to compile and install an extension in their root system won't be able to use a PHP extension. And we also have a experimental extension for Unicode normalization to guarantee that people aren't giving us a lot of bogus data as input text. And secondly, there is the search. Now, one of the reasons that we got into MySQL was that it had a search capability, but it's kind of slow. As you get more and more load and larger database, it requires more and more disk space, more and more memory to cache its index. Its index gets bigger and bigger. Today, the search index for the English language Wikipedia is at several hundred megabytes at least, going on a gigabyte, I think. And so that creates a pretty significant burden on the database servers. But having a search is an essential capability. So we've been setting up a experimental separate search system using Apache Lucene, which would run separately from the database and thus not bog it down. And that again would run as an extension to the system, which is optional because you have the built-in MySQL search. So that's an additional area where you can gain some extra speed if you have the if you have the ability to add it, but you still have compatibility when you don't have that ability. And that appears to be the last thing in my slide. Now, one of the other issues that we have is simply the amount of disk space used. I showed the graph earlier with the exponential growth problem, and that was just in the number of pages. But every page has been edited some number of times, some a few times, some a few thousand times. And we are keeping every revision because you never know what CRUD has been added, and you want to be able to go back to those earlier revisions and see who added what, and maybe revert to an older version. Plus, it's simply interesting to have, many years worth of revision data as a historical interest. But that takes a huge amount of disk space. And Tim is going to go into that and how we intend to solve that.
Like Brian said, I'll be talking about data storage and compression, and the huge amount of space storing all of the revisions takes up on Wikipedia now. Now, like Brian said, they've been growing at a phenomenal rate, and Brian showed the growth in the number of articles. And the number of articles has been doubling roughly once every 9 months or so, but the database size has been doubling every 16 weeks. I've got a semi-log plot here. You can see that that's a nice straight line, so it's well fit by an exponential curve, and it's been doubling every 16 weeks for the last 2 years at least. And it's now MediaWiki is designed on the principle that hard drive space is cheap, and we never thought that this would be a problem. You know, a few dollars per gigabyte or something like that, whatever it is these days. And we've always looked to attempt to get the minimal development time, since we've only ever had a few people working on this. So each revision is stored separately, and up until January 2004, everything was completely uncompressed. We now compress individual revisions for a 50% saving, but a 50% saving isn't really good enough, as you're about to see. One of the problems is that in MySQL, all of the data has to be stored on every single slave server, and we've also got on our master server, we have a RAID array, so that the database is stored maybe 8 times. So yeah, here's our hardware. We have a master database server worth $12,000, and it has an effective storage capacity of 200 gigabytes. And our database is currently 170 gigabytes. And if you add in the operating system files and a few log files that you need to keep for a while, it turns out that we've only got maybe a week of growth left. So this is a bit scary. If I wasn't at this conference, I'd be frantically trying to compress everything down, but no, I had to be here. And there's no more drive bays left, so we can't just add more drives. We'd have to buy like just a bigger server. But luckily there's another way. We don't have to spend money just yet. Instead of storing complete revisions, why don't we just store the differences between revisions? You might expect that to be a lot smaller. The canonical example of differential storage is RCS, the Unix utility. Now, RCS stores the current revision in full, and then it stores diffs to go back to each other revision. Now, RCS isn't necessarily perfect for our needs. RCS is designed to store code, and it has a simple ASCII data format, whereas we really want the best possible compression ratio. We don't need readability. The database rows aren't readable anyway. We've got them compressed with gzip. So what I was interested in is, can we do better than RCS storage? Wiki articles have a lot of long lines, unlike programming code, because usually a single line is an entire paragraph, and you get a lot of small changes. Here someone's corrected a typo in a paragraph, and so it's better if we don't have to duplicate the whole line in our differential storage system. Also, you often get edit wars, where two people will attempt to assert 2 different revisions. And these 2 revisions can be quite different. They might have deleted sections. Sometimes people even blank the page repeatedly. This would be a disaster if we used RCS for storage, because it would be slightly worse than what we're doing now. And on a slightly more minor point, what happens when someone moves a paragraph from one place to another? An ordinary diff it'll have a deletion command and it'll have an addition command, and so that paragraph is repeated in our storage. So what we really need is an algorithm which will recognize arbitrary sequences of bytes in one revision that are repeated in another revision, and it'll store them in such a way that we only have to store them once. And that just happens to be what compression algorithms such as LZ77 do. Yeah, LZ77, it makes up a dictionary of data patterns, and it uses Huffman tables to store those patterns efficiently. So we came up with the idea of concatenating revisions into chunks and then compressing the resulting chunks. And a good compression algorithm will take advantage between the it will take advantage of the similarity between those revisions, and it'll compress them with a very, very high compression ratio. So to test this theory, we did a proof of principle experiment. We compressed 3 articles with very long revision histories. One of them was an article, Atheism, with lots of edit wars. It's always contentious. Cleanup, which is a discussion page, one of the most active discussion pages on the wiki. And Physics, which is a more typical article, although perhaps it's been vandalized a lot since it's fairly high profile. So we expect better than average compression ratios for these articles with very long histories. And what we found was that we got a very good compression ratio indeed. With either gzip or bzip2, we got 2 to 2.5%. We got a final size of 2 to 2.5% of the original size. So that's a compression ratio of 97%. And we also compared it against an RCS-like method, which, as you can see, RCS performs very well for the discussion page where the text is just added to the end, but it doesn't perform so well when there's edit wars or even in the more usual case. Other tests we did showed bzip to be better than gzip. Well, we all know that, but bzip is a lot slower, and so we decided to go for gzip because our CPU time is at a premium. The test that we did probably wasn't fair to the diff algorithm, since we could have improved it a bit by working out what the closest revision was to a given revision and calculating the diff against that. And it also seems as if diff would be faster than gzip or bzip, but it's harder to implement, so we decided to go for gzip first. We've implemented a gzip method. It's out in MediaWiki 1.4, which, as Brian said, has just come out on the live site. Compression is hopefully taking place as I speak. I haven't had a chance to test this, given the state of the network here at the conference centre. We expect, because there'll be smaller data, we expect there to be better utilisation of the kernel cache, but there probably will be higher I/O bandwidth because to retrieve a single revision, a random revision, it requires you to load the whole chunk. And of course smaller DB size, which, as I've said, is extremely important at the current time. And we've been compressing wikis, we've been getting about 85% compression, so 15% of the original size. So in the future we're going to look at diff-based methods in a bit more detail. And also there's other ways to solve the space problem. I've said that we have a lot of redundancy, which is compounding our space problems. If we could have application level splitting across different servers, that would solve a lot of the problem. And another method that's been suggested is to put our data on a network file system, a distributed network file system such as GFS. And that's the end of the talk. Are there any questions? Yep. That's right. Well, we can concatenate it in maybe chunks of 10 or 20 revisions. Yeah, we concatenate all those revisions together and then run the gzip algorithm on them. Anyone else? Yep. That's with deflate, was that?
If we were to compress the results of the diff algorithm with gzip on top
Yeah.
of that. With that
Yeah, it
improvement.
could quite possibly be the way to go. The reason we haven't tried diff algorithms yet is it's just more complicated to do, because it's mainly more complicated because you need to handle a lot of different database rows. You need to load variable amounts of database rows for different revisions. Compressing diffs with gzip could well reduce storage quite a bit, but it's important to note that if you have an edit war situation, gzip compressing a diff which shows the difference between the adjacent edit war revisions isn't going to save you that much. It's only going to save you 50%.
Well, we probably could concatenate the diffs and compress them,
Yeah.
but then we would go
Yeah,
insane.
we'd have to concatenate the diffs. Yeah. Do we have... Can someone grab the microphone over there?
Did you ever think about combining the Mysql storage with a revision control system like Subversion or something like that? Because I think it handles the same problem,
Yeah, we have looked into Subversion. Well, we've had a cursory glance at Subversion, but we're not sure if it'll be fast enough for our means. Yeah, but certainly it's something we'll look at in more detail.
One of the possibilities that we might do is, because we're already starting to split the text itself from the revision metadata, would be storing the text in an entirely separate system instead of MySQL, such as an existing version control system, as you mentioned. So that is something that we might do in the future, once it's separated. And also, just a minor point, Tim mentioned application level splitting of the databases into smaller pieces. We actually have a very simple way to split our system basically in two, which is that each individual wiki is pretty much self-contained, and although we have theoretically several hundred, the English language Wikipedia is about half. The German and Japanese and a few others are pretty close seconds. So we could split that onto a separate server as a first step once things get too big for our current system to handle on each of an individual place. But eventually even that is going to get too big, which is where we'd really want to look at something like splitting the text out of the database entirely into a separate system. Okay.
Did you try a more space-efficient diff algorithm instead of textual diff like xdelta or such things?
No, we haven't at this time. Although xdelta, it should be noted, is slower than a line-based diff. Yeah, but it might be something to look at.
We've occasionally looked at xdelta for dealing with the large files like the public dumps of the database, because we actually release dumps of the entire encyclopedia databases for people to download and work with on their own or redistribute or just to have a backup in case our servers were to do that. But the problem with those is that just the files are too big and it takes a huge amount of actual in-core memory just to deal with them. But we haven't really looked at xdelta individually for smaller data such as the revisions. But that's a good point. We might look at it. Thanks. Well, if there are no more questions, stick around. Next up should be Jimbo Wales presenting on the sociological amazing things of Wikipedia. So if we have bored you with our technical talk or not, then there's more non-semi-technical stuff coming. Last chance for questions.